All right, so today we are going to talk about Chapter 7. Chapter 7 is about scatter plots and about correlation. Scatter plots you've probably seen before. A scatter plot is just kind of a visual um, representation of a graph of data. So a scatter plot looks like that. Essentially, you're comparing two different sets of data. In this particular case, looks like we're comparing the GDP with life expectancy. And then you plot your points on a graph, an XY axis. So this is a scatter plot. Your X variable, in this case, the GDP, is known as an explanatory variable. Explanatory sounds like explain. And your Y axis variable, in this case, it's life expectancy, is known as the response variable. The way I remember it is the response variable, the y-axis variable, responds to what the x-axis, the explanatory variable, does. So that is a scatter plot. Here's another example of a scatter plot in which we're comparing the looks like pizza toppings. That I took this from the textbook. We're comparing pizza toppings with the price of a pizza. So you can see our x-axis, our explanatory variable, is the number of toppings, and then the response variable, the y-axis one, is the price of a pizza. And you can see this is a positively sloped scatter plot. So in general, the scatter plot shows that as we increase the number of toppings, the price will also increase. And that certainly makes sense, that if we have more toppings on a pizza, that the actual cost of the pizza is going to be higher. When we interpret scatter plots, there are kind of three really important characteristics that we want to look at. Just like when we were looking at distributions, we looked at the shape, we looked at the center and the spread. With scatter plots, there are three different important characteristics that we want to look at. The first is the form or the association of the scatter plot. In other words, is it linear or roughly linear in nature, or is it curved? A scatter plot will never be perfectly linear, but does it form a roughly linear pattern? If it doesn't form a linear pattern, then we call it a curved form or a curved association. Now, I know you all know that there are many different types of curved forms. We could have quadratic, we could have exponential, we could have logarithmic. There are many different types of curved associations, but I just kind of took all of those and lumped them together as curved. So the form of a scatter plot, or the association of a scatter plot, is whether it's linear, whether it's roughly linear in nature, or whether it's curved. The direction, when we talk about the direction, we talk about, is it positive? Is it positively sloped? Is it negatively sloped? Or does it have no direction or no slope? And a scatter plot that has no slope will essentially look like, it just look like a bunch of random dots. So there isn't a clear pattern, a clear upward or downward pattern. So we would call that one that has no direction. So direction, is it positive, is it negative, or is there no direction at all? The last is the strength of the scatter plot. And when we talk about the strength of the scatter plot, we talk about how tightly clustered the dots are. So if the dots are very tightly clustered together, the scatter plot will be considered strong. Whereas if they're not tightly clustered, if they're spread out more, then we would consider that a weak scatter plot. Here's a couple of examples in terms of the strength. Okay, these are both of these scatter plots are clearly positively sloped in nature. They're roughly linear. Okay, they roughly form a linear pattern, but we can see the one to the left here, the dots are closer together. They're more tightly clustered, whereas the one to the right, they're more spread out. So we would consider that a weaker, we would consider the one to the left the stronger scatter plot, and the one to the right the weaker scatter plot in terms of the strength. Okay. One way that we measure the strength, sort of a numerical measurement of the strength of a scatter plot, is what we call the correlation coefficient. The variable R is what we use, is the symbol that we traditionally use for correlation coefficient. Right now, I'm going to talk about what it is and what it means, and then later I will talk about how we actually calculate correlation coefficients. So the correlation coefficient, like I said, is a numerical measurement of how strong a scatter plot is, but the catch is that it's only useful for a linear association. In other words, if you have a curved scatter plot, a correlation coefficient is not going to be useful in terms of telling you how strong the scatter plot is. A correlation coefficient is always going to be between -1 and +1. That's just how it turns out. I will talk about in a few minutes how we calculate it. But it's always between -1 and +1. And it's very simple. The closer that the correlation coefficient gets to +1, all right, if it's a positive correlation, that means that the scatter plot will be positively sloped. It will have a positive direction. If it's -1 or close to -1, it will have a negative slope or a negative direction. If the correlation coefficient is 0 or close to 0, then that means one of two things. It either means that the scatter plot is not linear, or it means that there's no pattern, meaning it just kind of looks like a bunch of random dots. Okay. So the closer that closer the correlation is to +1 or -1, then that means the scatter plot will be stronger. The correlation will be stronger. In other words, the dots will be more tightly clustered. It's just a matter of whether it's positive or negative. The closer it gets to 0, then the weaker the correlation is. That means the dots will be less clustered, they'll be spread out more, or they will form a nonlinear pattern. So basically, a strong correlation will be one that is either close to 1 or close to -1, depending on whether it's positive or negative. A weaker correlation will be one that's at 0 or close to 0, right? And that means that they'll either be less clustered, spread out more, or will form a non-linear pattern. The one useful thing about correlation that I haven't talked about yet is that if you change the units or if you use the z-score, it doesn't change the value of the correlation coefficient. What do I mean by this? In the textbook, there was an example where they measured the speed, the velocity of a bunch of cars going through an intersection, and they obviously measured it in miles per hour, and then they converted it from miles per hour to kilometers per hour. They changed the unit, miles to kilometers. And by doing that, the correlation coefficient did not change. Okay? As long as you convert every piece of data from miles per hour to kilometers per hour, the correlation coefficient does not change. It works the same with z-scores. In the last chapter, we talked about how to find the z-score. If we have a data item, we can find the z-score by subtracting the mean and dividing by the standard deviation. So if you were to take each individual piece of data, okay, and find the z-score of every single piece of data, and find the correlation between the z-scores, it would be the same. The point is, as long as you do the same thing to each of the data points, the correlation coefficient, the R value, does not change, whether it is changing a unit, like miles to kilometers, or whether it's changing everything to a z-score, finding the z-score of every data point. Okay, this right here is kind of a visual representation of what I was talking about on the previous slide. You could see if we start at the bottom here, we can see we have on the left-hand side we have a positively sloped. On the left-hand side we have positively sloped scatter plot, and on the right-hand side we have a negatively sloped scatter plot. And notice the one in the bottom right here. Okay, notice the dots are very tightly clustered. It's negative, and notice the correlation coefficient is very close to -1. Okay, and as I move up, the dots get spread out more, and thus the correlations get closer to 0. And the same thing happens on the left-hand side. Notice on the bottom left-hand corner, we have a positively sloped scatter plot. The dots are not as tightly clustered as the one over here, but they're still pretty tightly clustered. Notice it's positive 0.9. It's very close to +1, not perfectly, not exactly 1, but very close to 1. And as we move up the left-hand side, the dots get spread out more, and notice we have one of 0.5. Okay, and notice this one is 0. Okay, this one, the dots are really spread out. So this one ends up being 0. So this is kind of to give you a visual. I don't know about some of you, but I'm a visual learner, so it's always better for me to see a diagram of what something looks like. But this is what a positive versus a negative correlation will look like, depending on whether it's strong or weak. Okay, so some things to remember about correlation. Okay, like I said, it's only useful if we have a linear relation, a linear association. Okay, if the scatter plot has outliers, that outlier will have a large influence on R. Okay, so if you have a scatter plot in which all your dots are in one area, but you have one dot that's kind of off in the distance away from everything else, that outlier will have a large influence on the value of the correlation coefficient. And as I've said in the past, correlation does not imply causation. Okay, a correlation coefficient might show you that there appears to be some sort of relationship, but it doesn't mean that one thing directly causes the other. I'll give you a classic example of what I mean by this. There was an article that I read a couple years ago, and the author who wrote this article, had lots of data and scatter plots and all sorts of graphs to back up his claim, and he was basically trying to show that there was a correlation between the use of a lighter and whether someone gets cancer or not. We, of course, know that it's not the lighter that causes the cancer, it's the smoking that causes the cancer. So in that particular case, there was a correlation, but the use of a lighter does not directly cause someone to get cancer. So that's kind of an example, a silly example of what I mean by correlation does not imply causation. One of the things that you'll have to do on your Math Excel assignment is be able to match a scatter plot with a correlation. So here we have 4 correlations and we have 4 scatter plots. So when I am looking here, the first thing I notice is that 2 of the scatter plots are negative. So number 3 and number 4. And I notice that 2 of the correlations are negative. This one up here and this one over here. So that means they have to match with each other. Now the question is, which of the scatter plots which of the scatter plots are stronger? Well, scatter plot number 3 is more tightly clustered than scatter plot number 4, which means its correlation is going to be closer to -1, which means scatter plot number 3 matches with -0.9, and scatter plot number 4 matches with -0.4. Okay, so that was the first thing I noticed when I did this. I know I'm kind of talking a lot, but I want to model what I'm thinking so that when you do a similar example on your Math Excel assignment, you're able to do the problem. I also noticed with the 2 remaining ones, I notice that scatter plot number 1, which I outlined in blue, notice that it's not a linear pattern, it's a curved pattern. And we know that scatter plots that are nonlinear or have no apparent pattern have correlations closer to 0. Okay, so that means scatter plot number 1 is going to match with the 0.006 since that is the closest one to 0. Then obviously by process of elimination, that leaves 0.7 with scatter plot number 2. But notice with that one, that is the only one that's positive. And there's only so that actually leaves us with 0.777. Okay, so I kind of modeled for you here how I went through and how I did this problem. You will have at least one problem just like this on your Math Excel assignment. The last thing I want to show you, and then we'll be done, is actually how to calculate a scatter plot. We haven't talked about that yet. These are the directions on how to do that. I would certainly write them down. The key is when you open StatCrunch, you want to put the data in a column. And I will show you. I have some screenshots that I will show you how it works, so that when you have to do a scatter plot, you can get one. But these are the directions of how to do that. As far as how it will look in action, this is an example that I will quickly go through, and this is some data that I took from the textbook in which they were comparing the horsepower of an engine with its gas mileage, with its NPGs. So part A, using StatCrunch, make a scatter plot and use the scatter plot to describe the direction, form, and strength of the plot. So notice the first thing I did here is I put all of the data from here, I put that in a spreadsheet on StatCrunch. I put all the data for one column and all the data in another column. One of the cool things about StatCrunch that you can't do on, say, Google Sheets is notice at the top of each column, if you click on the top of each column, you can actually name each column. So I actually titled each column. I titled one horsepower, and I titled the other NPG, miles per gallon. So if you click at the top of each column, you could actually type in a title to make it easier for you. So that was the first thing I did. And then you can see here I went to graph, and then I went to scatter plot. And when I did that, this came up. And the important thing you want to do is you want to look at is these 2 things up here. These are drop-down menus. So notice for my X variable, I chose the first column, which was horsepower. And for the Y variable, I chose the second column, which was MPGs, miles per gallon. And when I click on compute, it actually gives me a scatter plot. It actually gives me the scatter plot for horsepower and MPGs. And we can see from the scatter plot, it's clearly a negative direction, right? I would say it's linear. It's not perfectly linear, but it's close to linear. And I would say in terms of the strength, I would say it's certainly not strong. It's certainly not weak because you can see the pattern. I would call it somewhere in the middle. So we'll call it a moderately strong linear negative scatter plot. Okay, so that's how we use StatCrunch to make a scatter plot. We also want to use StatCrunch in order to find the correlation coefficient. So again, if you have the data in columns, to find the correlation coefficient, to calculate it, you're going to go to Stat, you're going to go to Summary Stats, and then you're going to click on Correlation, obviously. Okay, so Stat, Summary Stats, and Correlation. And this comes up, and what you want to do is you want to make sure that you select both columns. You don't select just one column. So you may need to hold down the control button on your keyboard and make sure you select both columns, make sure both columns are highlighted. And then when you click on compute, it actually tells you the correlation. And you can see we get a correlation of negative 0.8, okay, which again makes sense considering if we go back to look at the scatter plot, it makes sense that we got a negative correlation because it was a negative scatter plot, a negative direction scatter plot. Okay, what does the plot say about the relationship between horsepower and NPGs? Okay, so remember that both the correlation and the scatter plot were both negative. They were negatively sloped. So what that means in the context of the problem, that means that as we increase the horsepower, that the mileage decreases, and that should make sense. The higher, the more horsepower you use, the more strain that puts on the engine. So your gas mileage is not going to be as good. Okay. Does this prove a cause-effect relationship between the two variables? In other words, does this prove that increased horsepower directly causes decreased gas mileage? Explain why or why not. This goes back to correlation does not imply causation. So yes, is horsepower a factor in affecting the gas mileage? Of course. It is one of the factors, but we know that it's not the only factor that affects gas mileage. So this does not, and that's a typo, that should say this does not prove, not improve. This does not prove a cause-effect relationship. Okay? This does not prove a cause-effect relationship. If we wanted to prove a cause-effect relationship, we would have to actually do a scientifically controlled experiment, and we will talk about that in future chapters. And that is it for Chapter 7.